Okay, welcome all. I will just show you how to do calculation for enlargement and contraction. Okay, so here is the raw data. This is for enlargement and this is for contraction. So for enlargement, H1, H2 you have measured. Okay, so you can see that H1 minus H2 is negative, which makes sense because of change in area. Increase in area increases velocity. Increase in area will decrease velocity and increase pressure, right? So H2 minus H1 minus H2 is negative. Uh, Now why this has happened? Because um, there is a change in area and we need to do correction. So velocity 1, velocity 2. So inlet velocity is flow rate divided by area, right? So 3.14 times this one area. This is small velocity. This is a smaller diameter. So this okay. So this is V1. Yes, yes, okay. And V2 will be V2 will be flow rate divided by area d square. These values are very small. I don't know why. Let me. Okay, let's continue. So V1, V2, and then correction factor delta H corrected, delta H corrected is delta H measured is this, right, minus. Okay, we have to add the term which is happening due to the change in velocity. So V1 square minus V2 square divided by 2 times G. Okay, so this is the delta H corrected. This is still negative. Okay, I think this is some problem in data. Okay, sorry, I had the mistake here. Velocity 3 is flow rate divided by area. Area is 3.14 pi over 4d square. Okay, so in both I forget to divide by 4. So now this is the corrected, which is delta H measured negative plus v square minus v1 square minus v2 square divided 2g. So this is delta H. So to find the loss coefficient, we need to divide delta H corrected, okay, divided by higher velocity. So delta H corrected v square over 2g. So v1 square 2g divided by delta H v square over 2g. So 2, so 0.648. So enlargement. So this is perfect. So you can see they are very close. So loss coefficient value are supposed to be very close and constant, right? So for the graph, you can plot delta H corrected this one versus Reynolds number. Okay, so Reynolds number is, we can take higher velocity times density times diameter. So smaller diameter we can take, okay, divided by viscosity 0.001. So you can plot K versus Reynolds number and you should get like constant value. So you can find the average value of this. Okay, and then standard deviation if you want to find, because we want to see how much is the deviation, which is standard deviation, this one, we should get very small number. So we can say that this is our average value with the deviation of 0.002, which is very less. So for all practical purpose, our rate constant value is constant. Sorry, not rate constant, this is loss coefficient. Okay, now for contraction, we'll do the same thing. So even we can drag this one all the way. Okay, so this one, delete this one. This is h1 minus h2. Ah, okay, sorry. So this is not. This is already in mm. The data. Let me see the data. Contraction. For contraction, h1 non contraction. Okay, so this is the data for contraction. So contraction, the data is this. Okay, and the formula will be the same one divided by 1000. Okay, so this is h1 minus h2. In this case, there will be extra pressure drop. Okay, so we need to subtract delta H corrected. Delta H corrected will be delta H measured, this minus, we will subtract. So this is okay. Wait a second. For this one, for contraction, this is V2. V2 is a smaller diameter, so velocity will be higher. Okay. So now correction will be delta H measured minus, we will subtract in this case, this square minus V1 square, okay, divided by 2g. Okay, so this is the corrected one. Delta H, loss coefficient K will be delta H corrected divided by, again we take the high velocity V2, so V square over 2g. 2g. No, no, this is V square Vs delta H delta H V square over 2g. So delta H divided by V square over 2g. So this is loss coefficient for contraction. Here we have a little bit of more deviation, but we expect this one also should be constant, right? So this is the average 0.81, deviation, standard deviation, standard deviation of this will be having a little bit more, yeah, so 0.18. So this is the average, and deviation a little bit more than, but it still makes sense. So we are around 0.81 and with the deviation of 0.18. Okay, so for the plotting, again you will plot delta H corrected for this one, delta H corrected, okay, versus okay, delta H corrected. This value is really low, 1.6. So delta H corrected is with V square over 2G. Okay, so this one is not here, right? So we need to calculate. Dynamic head must be calculated. Head, okay? Dynamic head is, and we'll take the higher one. So V square over 2G. So this one will be on x-axis. Okay. So this one on x-axis. So this is our graph. This value is really, so for sure you had some mistake here in reading these values. That's why these values are a little bit wrongly read. So that's why this is giving. You can see this one is good. So if we add trend line, linear, we can force intercept 0. Okay, so this one is as this 0.56. Okay, so this is all about calculation of contraction and enlargement. Thank you.